So in worked example 2, we have a particle projected horizontally with a speed of 15 meters per second. Okay, and that's all we're told. So what we have to infer from that is that the particle is going to descend, it's going to approach the ground due to the force of gravity and the acceleration it induces. So on the diagram that I've already prepared, we'll put a frame of reference on there. Again, I think we'll stick with taking the origin as the point at which the particle is projected. And again, it's up to you, but I'll take vertically as the positive direction, which is the y-axis, because it's so familiar and it's something you deal with day in, day out. So those are the positive directions. So x is moving in the positive direction to the right, and y is moving in the positive direction vertically. Let's write that on there. There we go. So let's have a look at the components. So horizontally, let's see what's going on. And you can do this for every question, irrespective of what you're being asked to do. It's the same process. So horizontally, in that positive direction, we have the 5 Suvat variables, and we also have the subscripts because we're talking about horizontal components only. So let's see what we can infer from the question. Well, we don't really know anything about the motion other than the fact that it's horizontal and it's traveling at 15 meters per second initially, because that's how it's projected. Okay. We also know, because this is common to all these problems, that the acceleration horizontally is 0. And that's about it. Other than for part A, we're asked to find its displacement horizontally and vertically. We'll get onto that in a moment. 3 seconds after the point of projection. So we do in fact know the time in this instance, and we needed 3 out of the 5 in order to answer anything using Suvat. So we'll write that in. So t is equal to 3 seconds. So it's that particular instant we're interested in. Right. So let's do some calculations. So we've got S is equal to, now we're going to use the most common formula, ut plus 1/2 a t squared, simply because that will encompass all the things that we know and the item that we want, which is the horizontal displacement. So we know all these things. So you just pick the equation that fits those criteria. So let's carry on with the calculation. So that means that Sx, in this case, the horizontal component of the displacement, is equal to ut, so that's 15 multiplied by the time 3. And we also know that that second term is going to be 0 because there's no acceleration horizontally. So therefore we have the horizontal component going to be 3 multiplied by 15, which is 45 meters. Okay, so that's good. So we've got the horizontal component as requested in part A. We still need the vertical component though. So let's have a look at the motion vertically under constant acceleration. So I've drawn my arrow going up like that. We've taken that as a positive direction. And we've got all our components in the vertical direction. So displacement, initial velocity, final velocity, acceleration, and time is a scalar. Okay, so vertically, well, we don't actually know the vertical displacement. That's what we're trying to find. The initial velocity vertically is 0. There's no vertical motion initially. It's falling, so it's 0. And that won't have a sign either because it's obviously 0. The final velocity we don't know. And the acceleration vertically is actually a deceleration, so that's negative 9.8 meters per second squared. And the thing that binds them together is the time. So we're interested in the time at 3 seconds. So again, we can use the same equation and find the vertical component now of the displacement, because it's that what we want. And we've got these components here. So it's exactly the same. and we're going to plug those into our Subat equation. So S is going to equal UT plus 1/2 AT squared. So SY, the vertical component, is equal to 0 multiplied by 3 plus 1/2 multiplied by negative 9.8 multiplied by T squared. Okay, oops, which is, we know that, don't we? It's 3. So I'll just replace that with 3. All right, so 3 squared there. And we just calculate this. So SY is going to equal negative 4.9 multiplied by 9. And we just do a little calculation on our calculator. Let's bring that up. And I'll just give myself a bit of space to do it. So this is going to be negative 4.9 multiplied by 9, which is negative 44.1 meters. Now it's negative because I've taken the positive direction to be vertically upwards. And because the particle is actually descending due to gravity, it's going to be a negative displacement. So we could add this to the diagram. We know now, and we knew that anyway, but we didn't know what the magnitude was. But we know that this is going to now be 44.1 meters, but that would just be after 3 seconds. So at this point here, it would just be T equals 3. So we don't necessarily know that it's touching the surface. So we'll just get rid of that. Okay. So now what we have to do is to figure out what the distance of the particle is from the point of projection. Now, this is important because we have to make a distinction now between distance and displacement. This word is not a throwaway interchangeable word with displacement. It means something. Okay. So let's investigate this a little bit further. So all that was part A on that side of the screen. Okay, now moving on to part B. So the distance of the particle from the point of projection. Well, from the point of projection, if this is the point after 3 seconds that I've just indicated with that mark right here, then the actual distance it's traveled in that time is going to be a straight line from the origin to that point, which I've indicated with a cross. Okay, so the way we can figure that out is by using the 2 components for displacement. And that's exactly what I'm going to do. So I'm going to use a small sort of reconstruction of the displacement. So we're going horizontally 45 meters, and we are traveling vertically downwards, which is perpendicular, 44.1 meters. And that hypotenuse there is the distance traveled, okay, from the origin. Now, it's not the distance along the path, it's the distance of the point from, of the particle from the point of origin, okay? Just want to make that clear. So the question states it's the distance of the particle from the point of projection, okay? It's not the distance it's traveled along its path. That would be a greater distance and would be represented by this arc here, but we're not figuring that out at the moment, okay, or at all in this example. So all we need to do now is a little bit of Pythagoras' theorem. Okay, so to find the distance, we'll call the distance d. We use Pythagoras, so d squared is going to equal 45 squared plus 44.1 squared. Okay, so we're going to use our calculator again. I'll just move it out of the way. Cancel that. So we've got 45 squared plus 44.1 squared equals close to 4,000, square root the answer, and we get 63.00. So it's close, very, very close to 63 meters. So therefore, D is going to equal 63.0 meters, and that's rounded to 3 significant figures. Okay, and we're done.